So we've talked about parametric parabola. We did a couple of examples involving parametric circles. Now we're going to talk about parametric lines. Example 4 says find a Cartesian equation of the line parametrized by x equals 3t plus 2 and y equals t plus 1. Now, whenever you see a parametric equation where x and y are both linear in t, that's always going to give you a curve that's really just a line. And one of the questions is the parameterization unique? Okay, so let's go ahead and see. Now, what do they mean when they say Cartesian equation? That's just a fancy way of saying an equation in terms of x and y. Okay, so I'm going to do the same thing that I did before. I'm going to solve the parametric equation involving x for t, and then plug it into the parametric equation involving y for t. So starting with x equals 3t plus 2, I can subtract 2 and divide by 3. That tells me t is equal to x minus 2 over 3. Okay. But now, since y is equal to t plus 1, and t is x minus 2 over 3, y is equal to x minus 2 over 3 plus 1. And then I might as well write that into slope-intercept form. So x minus 2 over 3, that's going to become x over 3 minus 2 over 3, of course, still plus 1. And I can now rewrite that as y equals x over 3 is the same as 1/3 x. Negative 2/3 plus 1 is positive 1/3. So there's my Cartesian equation. And then for the second part, is the parameterization unique? Well, it turns out that really no parameterization is ever unique. Okay, so the answer to this next question, is the parameterization unique? No, because you can let x equal t, and then that's going to be the simplest parameterization you can think of. And if x is t, y equals 1/3 x plus 1/3 becomes 1/3 t plus 1/3. So that's another parameterization. Or here's another one. Again, there's infinitely many of these. You could let x equal 2t. Well, then y is going to equal 1/3 times 2t plus 1/3. Okay, so there's there's infinitely many parameterizations now. You can choose any linear function in t for x, and then you can take the Cartesian equation and replace x with the parametric equation for x. So there's actually infinitely many of these. You can use any linear expression for x in terms of t, and then substitute that into the Cartesian equation for x to get the equation for y in terms of t. Okay, so in general, though, x equals at plus h and y equals bt plus k. This is going to give you a line with slope b over a that passes through the point hk at t equals 0. So if you come back to your previous parameterization, so from example 4, so notice from example 4, what we had was x was equal to 3t plus 2, and y was equal to t plus 1. Okay, in this example, right, x is at plus h. So in this case, a would be 3, h would be 2, and b would be 1, and k would equal 1. So the slope, again, we know that's a parametric line already. The slope is b over a, which we saw in the previous example was 1/3. and at t equals 0, the line passes through the point 2, 1. And you can see that right away. If you plug in 0 for x and y, you get 2 for the x coordinate, and you get 1 for the y coordinate. Okay, now parameterizing lines is easy. What becomes difficult is when you start parameterizing segments of curves, right? Because now we can do piecewise parameterizations where maybe from 0 to 2 seconds you have a line, and then from 2 seconds to 4 seconds the curve takes a parabolic or circular path. Okay, so we're going to find a parametric description or a parametric representation of the segment of the parabola y equals 4 minus x squared for x between -1 and +2. So now we're just looking at segments. Kind of go back to example 1, right? In example 1, we had a parametric parabola, and it was just for a particular segment of a parabola, namely the right half where x went from 0 to 8. So go back to the beginning of the video to see what I'm talking about there. Okay, now, anytime you're going to be given the Cartesian equation of the curve first, so an equation in terms of x and y, I always do the easiest thing. When I'm going to parameterize something, I just let x equal t. So I'm going to let x equal t. And then since y is 4 minus x squared, y becomes 4 minus t squared. And then since x and t are identical, my parameterization is just going to, or my value of t is just going to also be between -1 and 2. Okay, so that's one way to do it. Now here's another one. So what if I just wanted to get kind of silly and, okay, I want to let x equal 2t. Well, that means y then has to be 4 minus 2t squared. But now you have to think about what your range of t values is. X goes from -1 to 2. Okay. And maybe I'll write this down. I'll write this all down before I simplify. If x is 2 over t in blue, that means t has to be x over 2. Okay. And when x is -1, t is equal to -1/2. And when x is equal to 2, that means t is going to be 2 divided by 2, or +1. So in black at the bottom, I'll write this second parameterization. We can do x equals 2t. You can see that y is going to be 4 minus 4t squared. But now t is going to range from -1/2 to +1, because when x is -1, for that second parameterization, when x is -1, that means t has to be -1/2. And when x is 2, that means that t has to be +1. So again, we have infinitely many different parameterizations that we could choose for that parabola. It's just that each parameterization is going to give us a different range of t values. Okay. All right. Compare my two examples too, by the way. Like in the first one, x was t, and notice how t was between -1 and 2. When x is 2t, that means you're kind of making x go twice as fast, so your interval is just going to be half as big, right? So if I went from -1 to 2 before, I went from -1/2 to 2 divided by 2, or 1, when I doubled x. Okay. Here's another one where we're going to find another parameterization. Okay, now oftentimes, again, there's the parameterizations can be as simple or as complex as you want. I'll show you two parametrizations in example 6, one in purple, one in blue. So let's find a complete parametric let's find a parametric representation of the complete curve x equals y minus 4 squared plus the square root of y. Now, whenever they give you x in terms of y, it's easier to choose a parametrization for y first. And you can just do the easy one. Like the first one is, y. You can just choose y to be t, and then that means x would just be t minus 4 squared plus the square root of t. So all the y's become t basically. And then I guess you could say that t is between negative infinity and infinity. Although if y is going to be t and there's a square root of y in the expression, you can't use negative t values, so t would be greater than or equal to 0 there. Okay, so that's one thing you could do. So you could just choose the easiest parametrization you want and just let y be associated with t. The other thing you could do, okay, again, I could let y be 2t. Doesn't really matter. X would then be 2t minus 4 squared plus the square root of 2t. And again, t would just be greater than or equal to 0. So whatever I choose for y, to get the parametric equation for x, I just take the equation for x in terms of y and replace y with 2t or whatever you've chosen y to be. So I'll do one more in black. What if I said, okay, y is going to be 2t minus 1? Well, then x has to be 2t minus 1 minus 4 squared plus the square root of 2t minus 1. But for this one, again, 2t minus 1 must be greater than or equal to 0 because that's what I chose for y. So for this one, t has to be greater than or equal to 1/2. Or actually, yeah, greater than or equal to 1/2. So there's a third parametrization. So parametrizations are not unique. All right, so I have one more example. Okay, and last example. This time we're going to do parametric equations of a piecewise linear path. So what we're going to do is we're going to find a parametric representation of the piecewise linear path that connects the points P, Q, and R, where P has coordinates negative 2, 0, Q has coordinates 0, 3, and R has coordinates 4, 0. And again, in that order, where the parameter varies over the interval from 0 to 2. So first, let's draw a picture. And just plot these points P, Q, and R, and then draw a picture of the parametric curve or the parametric piecewise linear path. Okay, so I need a little bit of space in the negative direction. Okay. And there we go. So I'll go 2 units to the left. I'll go up 3 units. And I'm going to go to the right 4 units. 1, 2, 3, 4. Okay, and let's go ahead and use purple for the path. So the point P has coordinates negative 2, 0. The point Q has coordinates 0, 3. And the point R has coordinates 4, 0. So here's the curve. I'll include the arrows to indicate the orientation. Okay, so I have P, Q at 0, 3, and R at 4, 0. Now, what I generally like to do is there's really just 2 linear paths here. There's P to Q, that's one linear segment, and then there's Q to R. Usually, if it's up to me, I usually make each piece that you travel on take 1 second of time. So what we're going to do is we're going to travel from P to Q for t between 0 and 1, and travel from Q to R for the interval 1 to 2. Okay. The next thing is, remember the equation of a parametrization. If you want to start at the point -2, 0, so it's the easiest thing to do is to parameterize the curve from P to Q. Okay. It gets a little bit more difficult to make sure that you can parameterize from Q to R, but also make sure that it traces out that segment of the curve between 1 second and 2 seconds. Okay, so from P to Q, the way this is going to work is we need to know the slope of the line, and we need to know our starting point. Now the change in the, here I'll write down the general parameterization in blue again. So generally it's x equals a t plus h, y is equal to bt plus k, where the slope is b over a, and at t equals 0, we start at h comma k. Okay. So, I'll write it down for P to Q, and then I'm gonna have to write it somewhere else to make more room when I find the parameterization of Q to R. Okay, so let's say I'm doing P to Q. Okay. And I want to start at P and end up at Q after 1 second. Looking at the picture, I'm going to use red. To go from one point to the other, right, there's a horizontal distance and there's a vertical distance. The horizontal distance is going to be A, and the vertical distance is going to be B, because the slope of the line from P to Q would be rise over run, or B over A. So coming back down to the bottom right, and actually let me write that in purple. So if I'm going to parameterize P to Q in that direction, sorry, I'm kind of using the vector notation here, but I think that's okay. So x is going to equal, it's at plus h. Okay, h is the x coordinate of where we start. And a is going to be the horizontal distance. So x is going to be 2t minus 2. Y is going to be, well, what's the vertical change going from P to Q? We went up 3 units. So it's going to be 3t, but then plus k, the y coordinate of where we start, which is 0. So we're just going to get 3t. And this, you can double check it, but that's going to be on the interval from 0 to 1. You should verify that when you plug in 1, when you plug in 0, you get the coordinates of P, which you do. You get -2 for x and 0 for y. And when you plug in positive 1, you get 0 for x and 3 for y. So there's the parameterization of the segment from P to Q. Okay, now I want to go from Q to R. Now let me write that, let's see, where's the best spot to write it? So I'm going to just erase what I had in blue there. And I'm just going to rewrite this. Okay, so we have P to Q. Now, let's parameterize the path from Q to R. Now, again, here's the one thing that's tricky. This time, it'd be a lot easier if the time interval was still 0 to 1. Okay, but unfortunately, the time interval from Q to R has to start at time t equals 1 and finish at time t equals 2. Now, a little trick for this is you're going to still use the same idea for A and H. And again, I'll write the general form at the bottom. X equals AT plus H, Y equals BT plus K, where again, B is the rise, A is the run, and HK is the starting point, or the coordinates of the where the segment starts. Okay. Now, for X, and here's the trick. Normally it would be AT plus H, but that's when you start when your interval starts at 0. When your interval starts at 1, what you have to do is replace t with t minus 1. If your interval was starting at 2, right, if you had a third segment and it started at t equals 2 seconds, you would use t minus 2 instead of t. Now, the rise and run, to get from Q to R, you have to go 4 units to the right. So for x, we're going to do 4, not t, but we're going to do t minus 1, plus the x coordinate of where we're starting, which is 0. So it's just 4 times t minus 1. The y coordinate is going to be, let's see, so from going from Q to R, we had to go down 3 units. So it's going to be negative 3 times t minus 1 plus the y coordinate of Q, because that's where we started with. That's 3. And the interval for t then is 1 less than or equal to t less than or equal to 2. Okay. Now you should be able to verify. The only thing you need to check is on the segment from Q to R, just make sure that when you plug in 1, you get the coordinates of Q. When you plug in 1 for x, you get 0. That's good. When you plug in 1 if you plug in 1 for the equation for y, t minus 1 becomes 0, and you just get positive 3. That checks out. And then when you plug in positive 2, you get 4 for x, and you get 0 for y. There is your piecewise, the parameterization of your piecewise linear path, first from P to Q, and then from Q to R. Okay, and if there was a third path, we would just have a third piece. Then we would have a third parameterization, probably on the interval from 2 to 3. But in that parameterization, you would replace t with t minus 2. Okay, that concludes the video. A little bit of a long one this time. Thanks for tuning in. I hope you all have a great rest of your day. I look forward to seeing you. Take care. Until next time.